Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh, and good day everyone. We are still learning about the topic of exergy. This is the first chapter for BMCG 3713 Thermodynamics 2 exergy. Right, before this we learn about definition of exergy and how is exergy defined in every state during a process. Now we are going to look at exergy transfer. Exergy transfer. In general, starting from this video, this topic, we're going to look at interactions of exergy. Exergy interactions that represents interaction of the system with the surrounding. Okay. Right. Let's revisit the energy balance equation. This is the energy balance equation. Energy that enters the system minus energy that leaves the system must equal to energy change of the system. So energy that enter the system and leave the system can be in a form of heat transfer, work, or mass. Okay, for open system we have mass transfer in and out of the system. Right. Almost the same principle is going to be applied for exergy. What is the difference between energy and exergy? Do you still remember? Energy is the form of power, energy, but exergy represents work potential. It is energy, yes, but it is only representing the energy that can be put to good use. Okay, the work potential. Right. So in similar way, energy balance is considered. We're going to have to consider almost the same principle in exergy analysis. Therefore, we need to identify equation that represents exergy transfer by heat, exergy transfer by work, exergy transfer by mass. Remember, we are talking about interactions between system and surrounding. Before this, we talk about exergy change within the system at initial state, at final state, at state 1, at state 2, during a process. But this time, we're going to look at interactions between the system and the surrounding. So that needs to be analyzed based on exergy change in state as well, yes. But in addition to that, we need to also consider exergy transfer. So exergy transfer can happen by heat, work, and mass. Right, the equation that we need to use for exergy transfer by heat is this one. So that's the equation that represents exergy transfer by heat. The equation comes from energy balance, but we need to remember this because we are going to use it. Exergy transfer by work is this, the work plus minus the surrounding work. We have talked about this before. And then exergy transfer by mass is simply this equation, which is exergy transfer in that state. For example, this is state 1. Okay, and in state 1 there is mass transfer crossing the boundary. So this is exergy transfer by mass. So the equation that we considered before in the previous video are mostly related to this part, exergy transfer by mass. Right, so this is the exergy balance, everyone. This is exergy balance. We need to consider exergy transfer by heat, by work, and by mass. And this represents exergy that enters the system and exergy that leaves the system. Right? The difference between exergy that enter the system and exergy that leave the system must equal the exergy change of the system. What happens if it is not equal? Like the energy balance. Heat enter the system as 10 kilowatt, leave the system as 8 kilowatt. So what happened to the rest? The 2 kilowatt, for example. What happened? Right? It is lost. And in the topic of entropy, in thermodynamics 1, we learn that losses may be related to entropy generation. But this time, we're going to learn these losses. This is the losses or the the imbalance of the equation as something that is known as exergy destruction. If you remember from video that we learned before, there is a term known as exergy destruction or irreversibility. Okay, the losses. Right. So we have two boxes in this equation. This is the first box and that's the second box, two boxes. To highlight that the equation that we studied before in the previous part related to exergy equation in states and exergy for a process. Okay, those equations are going to be useful for these two parts. Why? Because in the first part, this is the first part. This is the first part. So in the first part, we are talking about exergy by mass that enters the system and exergy by mass that leaves the system. So we are talking about state 1 and state 2 at entrance and at exit. So the exergy difference represents exergy change by mass. So how do we consider this? Depends on the system. So usually when we talk about mass balance, the system that we are talking about is the open system. Okay, the open system. If you recall from previous topic, we recall that exergy change for an open system is enthalpy change, T naught multiplied by entropy change, the kinetic energy, and the potential energy. Okay, this is between inlet and outlet. Right. The second equation on the right side here represents whether the system is steady or unsteady. If it is unsteady, it means that there is a change between final state and initial state. This change with respect to time. Final and initial is about time. Inlet and outlet is about location, space. Final and initial is about time. Okay, so at final situation and at initial situation, will the exergy be the same? If not, then the system is running in unsteady situation, transient situation. So if that's the case, there will be exergy change due to the change of properties in time. And that exergy change with time is represented by this equation if we are talking about open system again. The same equation of exergy change, but this time we are talking about time, final, initial. Final, initial. Final, initial. See? Final, initial. But still, we are talking about enthalpy, the first term, entropy change related to heat transfer, kinetic energy, the third term, and the potential energy. Okay? So we are okay with these two terms with respect to inlet and outlet, this one, and then with respect to final and initial, that one. What happened to this? Energy transfer across the boundary. Okay, these terms are representing energy transfer by heat. Okay, where is it? I need to highlight this. Okay, energy transfer by heat crossing the boundary. Energy transfer by work crossing the boundary. How do we calculate that? Using the equation that we saw earlier. Okay, and this is exergy transfer by mass. Okay, right, so this is the introduction about exergy decrease. Exergy decrease. What is exergy decrease? Sort of the irreversibility of the system. If it is reversible, reversible means ideal. Reversible equals ideal. Okay? Then there will be no exergy destruction. Remember? Exergy destruction, irreversibility. It leads to no irreversibility, which means that we will end up with the first term, second term, third term, and the fourth term. That's it. This becomes 0. But if the system is irreversible, there will be losses. Okay, something that we cannot avoid. For example, in the real system, okay, there will be losses, and these losses leads towards irreversibility or exergy destruction. Exergy destruction. This is introduced here, exergy destruction or exergy destroyed. So how do we calculate exergy destroyed? It relates to irreversibility. That's something that we must remember. One way of doing this is by using the equation that we saw in, I think, the first part or the second part of the video, where irreversibility is basically the reversible work minus the used work. This is one way of calculating exergy destroyed. But how else can we do the calculation? How else can we do the calculation? Let's look at the decrease of exergy principle. How to calculate this exergy destroyed? Right. The calculation is related to entropy generation. Entropy generation. Right? So if you don't remember the topic of entropy generation, please do a revision related to the last topic of thermodynamics 1, entropy. Okay, so we learned that entropy can be described by this equation. The change of entropy is basically heat transfer divided by the temperature of that system. Okay, so this is entropy. But exergy, X is exergy, everyone, is defined this way: 1 minus ratio of T naught over T, and then the whole term is multiplied by Q. So what's the difference between exergy and entropy? The equation is different. Therefore, when we represent losses in the real system, if the losses is represented by entropy, we are talking about entropy generation. Remember, in the topic of entropy, we learned that entropy cannot be destroyed. It is always increasing, entropy generation. However, if the losses is represented by exergy, the work ability, it is going to be described as exergy destroyed. The value is reducing, exergy destroyed. Okay, and the exergy destroyed is represented by this equation. Exergy destroyed is T naught multiplied by S generation. So this is another way of calculating exergy destroyed. Of course, you can calculate exergy destroyed by the equation that we have before, reversible work minus the used work for turbine. If it is a pump, then it is going to be used work minus reversible work. I hope you remember this. This is one way of doing it. Another way of doing it is by considering this equation. Exergy destroyed is also T naught as generation. Okay. For reversible process, exergy destroyed should be 0. This is common sense. There will be no entropy generation. There will be no exergy destroyed because it's reversible. But in actual process, the exergy destroyed, which is calculated as T naught multiplied by entropy generation, is going to be bigger than 0. That is irreversible process. Right. So this is the equation of exergy destroyed. We know the relationship between exergy destroyed and entropy. How are we going to apply this into equation? How do we calculate entropy generation? So entropy generation comes from this equation, the entropy balance. Okay, so this is entropy balance. Entropy that enters the system minus entropy that leaves the system plus entropy generation is the entropy change of the system. So this will be 0 if it is a steady process. If not, then it's not 0. Okay, right. You can always look at the topic of entropy to do revision related to this. So entropy in and out can be represented by this equation. And that equation can be further explained by these two boxes. Okay, this is entropy by mass, and this is entropy by heat. Entropy transfer, by the way. Okay, and then the balance of this equation will lead us to an entropy generation. Okay, now let's have a look at how we apply Exergy balance into closed and open system. Remember, closed system is system that doesn't allow mass to leave the system or enter the system. Open system is the system that allow mass to leave and enter the system. That's the difference between the two. Okay, therefore open system carries flow work. Okay, so the Exergy balance in general can be described as this. Exergy that enters and leaves the system minus exergy destroyed must equals the change of exergy in the system. Almost the same definition as given in entropy balance. So this is general exergy balance. If we expand the equation, try to understand what is entering and what is leaving the system, we will then identify that exergy transfer can be in a form of heat, can be in the form of work, and it can also be in the form of mass. So these three terms represented by the red bracket here is representing exergy transfer. And then this exergy destroyed is related to entropy generation, the irreversibility. Okay, irreversibility or entropy generation, TS gen. This is exergy destruction. How about exergy change? This is the change of exergy with respect to time. See, if it is a steady flow system, it doesn't change with time, the exergy or the energy. Then the exergy change with time is 0 for steady flow. If it is not steady flow, then you need to consider the initial and final situations. But exergy by mass is representing the inlet and outlet situation, the states. Okay, the equation that we saw before related to enthalpy change, and for an example for open system, this becomes enthalpy change plus T naught S 2 minus S1, for an example, if we neglect kinetic energy and potential energy. This is not plus, but this is minus. Okay, for an example. Or for a closed system, it could be the change of internal energy plus P naught, the change of V, minus T naught, the change of entropy. So it depends on whether we are talking about open system or closed system. If you talk about work transfer through the boundary, we are talking about moving boundary most of the time. Okay, so it's the work plus or minus the surrounding work that the system needs to overcome, or when the if there is any. Okay, and then for heat, this is the equation: exergy transfer by heat, 1 minus T naught over T multiplied by Q. So try to understand these equations and its relationship into the exergy balance equation, so that we can use the equation many times in solving analysis. Okay, let's have a look at this example, a very simple example. There is no calculation involved here, but we need to identify what is the equation that we can consider in this problem. Okay, based on general exergy balance equation provided, derive the specific exergy balance equation. Okay, the specific exergy balance equation for the system shown in the figure. So we can see that this is a closed system. That is something that we must understand. And then the component of work that leads to an exergy, if you have exergy by work, because the boundary is moving, and in doing so we have the change of exergy in the system. This represents probably state 1 to state 2, for an example, the change of exergy. And then there is also exergy destroyed being described here. So this is not ideal system, this is real system, actual system. Something is lost. Okay, exergy destroyed. And we can see that this expansion process is happening because of the heat transfer. So how do we consider this? We know that this equation can be represented by exergy transfer by heat. Please look at your notes and then look at how this can be represented. And then this is exergy transfer by work. This is exergy transfer by mass, which is related to this. And then we have Exergy destroyed, usually represented by T naught as generation. And then we have the change of Exergy in the system. Okay, so if this is a steady system, if we assume that this is a steady system, then this becomes 0, for example. So if we say that this is a steady system, and then everything that is being described in the picture is there, so we may end up with this component, energy transfer by heat at the boundary. So that will give us 1 minus T naught over T multiplied by Q. Right? Q is the amount of heat here, and then T naught is representing the temperature at the dead state outside, T naught, and then T is the temperature inside the system at the boundary, basically. And then we have the component of work. We know that the boundary, this boundary is moving, expanding, for example, in this case. So we have equation of this is heat, and then work is being supplied to the surrounding. So we have work out. So negative the boundary work minus P naught V, I don't know, V2 minus V1, for an example. Okay, if we say that this is state 1 and state 2. Because the boundary work need to overcome the pressure of the surrounding. That's why we have this. And then we have this equation, Exergy transfer between state 1 and state 2. Is there a state 1 and state 2? We may not be having this, but we may have the change between initial and final situation, because this is probably not steady. Okay, probably not steady, but both are going to be represented by almost the same equation. Okay, so this part is represented by, because this is closed system, it is represented by delta U plus P naught delta V plus, minus T naught delta S. Okay, so that could be representing this mass. Okay, so I'm going to write that as XF in this situation. And I have Exergy destroyed because that is being described. It says that there is Exergy destroyed here. If I say that this is a steady system, the right side of the equation becomes 0. If it is not steady, the operation change with time, then it's not 0. Okay, so this is one example that we can consider for this topic. Right, so this is basically the end of this part 5. So we are going to continue discussing about Exergy in the next video, inshallah.